Okay, hello to everyone. We are Machine Learning Together Milan. Today we are with Andrea Megaro. We are talking about supervised clustering for time series, and this is the third meetup, sorry, with Andrea. And we are talking about okay, so we are talking about unsupervised learning, okay, but is in this particular field called time series. So we are trying to do some clusters with time series using an unsupervised approach. We have seen different metrics, different kind of create the groups. We have and today we want to finish this big topic and start with some practical exercises or notebook to use all these techniques in our everyday life in machine learning, because this is the topic.
Yes.
So,
yes,
hello, Andrea. This is your turn.
Thank you, Julien. Yes, as you said, maybe you have to allow me to share the screen.
Oh, yes. So, sorry, as usual.
Okay. Yes, as Julien said, this is the last meetup about unsupervised learning with the focus on the time series, multivariate time series. And in this meetup, we will talk about the practical approach that we can use on Python and R. So let's begin with a brief introduction of what we said last time. So this is the topic, unsupervised learning. This is me, Andrea Megaro, CFO of Gymnasio, and I will not spend any time about the description of Gymnasio that
is the best one.
Maybe is enough the time spent last time. This is the table of contents, and we arrived to the chapter 4, complementary techniques. What we have seen, unsupervised learning, theoretical background, and so all the differences between supervised and supervised techniques, the focus on the time series clustering, and so we focus on unsupervised technique that are applied to the time series clustering analysis, in particular the one about the shapes. So we cluster time series window based on their shapes. What is the objective? The objective is to cluster different windows of multivariate time series according to a metric. But what is the best way to cluster these windows? And we talked last time about all the cluster goodness evaluation parameters. This time we will talk about the complementary techniques, and so the practical approach that we have to keep in mind before starting any type of any analysis of this type. And then there will be the description of the case study, and finally in chapter 6 we will see the take-home lesson. Not lesson, but lessons. So there will be at least 5 or 6 points that I will stress on. So let's begin by the 4th chapter. So this is briefly maybe I will see briefly the chapter 2 where we saw the difference between shape-based and feature-based approach. We chose the shape-based approach, and we described the two distances that we will see in the practical part, and so the dynamic time warping and the shape-based distances. So keep in mind these two distances. If you don't remember the difference or the details, you can also see the recorded lessons in the YouTube channel. What is the definition of prototype? A prototype is the representative of one cluster of windows of time series. And so we saw the three different types of creating a prototype. We saw the PAM, the shape extraction, and the DTW barycenter averaging. And then we saw the principle of CVY. And so the way to evaluate the goodness of all different clustering that we have done according to the measures and the prototypes types that we chose. So now we will see what we can do before this analysis in order to create my starting data set and to create the basis of the following case study. So I focused on three basic ideas. The first one is related to the time frequency analysis that we can do before the division in windows. And so the main problem that we are talking about is the resampling techniques. So we know that a certain signal can be noisy or very, very clear. Most of the time when we are talking about real data, the data series are very, very noisy. So this first part of this chapter is dedicated to all the time frequency principles that we can apply in order to reduce this noise. Then we will talk about the correlation between the same or other time series in order to delete some series that are really correlated with others in order to not to repeat some information. And then there is the fatidical question, how can I choose the right length of the window? So we will talk about one single paper, but this field is full of papers about different ways we can apply. I will focus on this one because it is really specific for big data. Indeed, this paper focus on the speed of evaluation of this optimal length. And so let's begin. Time frequency analysis. This chapter is based on the famous book Foundation of Signal Processing. You can see it everywhere. I will talk about a few concepts that introduce you to this very mathematical topic. If you don't want to deep on this topic, I can understand it because it pretends you to have a strong basis on math. I will give you only the intuition. I will suggest you to read this book because it is very, very intuitive, also for non-mathematics, but I can understand that for non-mathematic people can be very boring. So let's introduce the main concept, the one also very specific to the case that we will talk about in the next session. So what is the CN space? The CN space is the space formed by all vectors, so a list of numbers for informative people, a list of numbers x0, xn minus 1 that we can normalize with the p-norm defined as the one that you can read in the slide. What is the jump into the infinitive space? The LPZ space. So in which we have an infinite length list of numbers that you can normalize in this other way. The main difference is that in the first case you can give an order, so n goes from 0 until n minus 1. In the other case, it is unordered. So what is the definition of normed space? A normed space is the subspace of CZ consisting of vectors with finite LP norm. So if you group all the vectors with infinitive length and you take only the ones that have a finite norm, LP norm, so you can consider this one the LPZ space with a normed vector space. If we add also the inner product, we are creating a LP norm inner product space. And if we add the property of completeness, so we can define this space a Banach space if it is complete and normed. If it is complete and inner product space, we can call it a Hilbert space. All this sequence of slide is only to say that the most important signals can be treated within the Hilbert space, and all the concept in the previous mentioned book are inserted in the concept of Hilbert space or Banach space.
Andrea, so, I only want to do a brief
yes,
a brief idea. An Hilbert space, it's only the general definition for an infinite dimensional space, but in general, but in particular, when we talk about Hilbert space in finite dimensional space, we are talking about the classical Rn. So classical where an element is an n tuple, okay?
Yes.
And when we are talking about an Hilbert space in infinite dimensions, we're talking about a function that can be seen as a decomposition in like in Rn, where we have the similar basis. Okay, it's
this is the topic that I will.
Okay. It's but it's you have to see the Hilbert space in infinite dimensions for a signal as the generalization of the Rn.
Yes, exactly. Yes, this is what the concept that I want to stress with this slide. Maybe it is not the one that is passed, but yes, in this space we are considering a generalization of the simple CN space. But why I'm talking about this? This is only to introduce you to the decomposition of vectors with a series of other vectors that are called bases. So we can decompose every single vector in a general normed vector space V as the linear combination of all the basis vectors multiplied by some constants that in this case are alpha j. If we have all the vectors of the basis that are orthonormal, we have an orthonormal basis that fully describe this Hilbert space vector. Why I'm telling you this all this stuff? The reason is simple. To introduce this theorem, the Ritz theorem. This theorem is telling you that if you want to describe any signal in the space that you are considering, that can be finite, infinite, or any Hilbert space that you want to consider, you can describe this space through a decomposition or through other orthonormal vectors that form the basis, and you can also do the inverse operation. So you can do a transformation with this basis and the inverse operation to come back to the original signal. Why I'm telling you this? The reason is that you can describe with a series of functions and multiplied by a series of coefficients every single signal in a certain space, in particular Hilbert space. The most famous case is the Fourier decomposition. So in order to describe a signal in an Hilbert space, you can use the Fourier basis, and the Fourier basis in this case is described by the finite basis for the case Cn to Cn, the one described in the slide. And you can, with the proper combination of coefficients, you can describe every signal in Cn through this decomposition. Why it is important? The reason is summarized in this slide. Let's consider the blue signal, the one in the time domain, in the left hand, in the left part of the picture. So the blue signal can be one signal of any signal in a certain Hilbert space, or as Julien said, Rn space. We have this signal and we want to delete the noise that it contains. How can I do? Well, according to the theorem that I described before, we can decompose this signal, this series, into different, into all the vectors of the basis of the Fourier basis. So as we can see in the frequency domain, we have two frequencies that fully describe the signal in the time domain So we can understand that the signal in the left part is described by, for example, in the figure on the right, 60% from the first component and 40% for the second component. We can see that the second component is smaller in percentage with respect to the first, and that it contains all the noise that we wanted to delete. So there is a way to delete only the small waves created by the second signal, the signal that contains all the noisy information, and to preserve only the information that we are interested on. So in this way, we are applying a low pass filter. That is exactly what I said now. And so we want to delete the noisy part that is most of the times contained into the high frequency domain, and to preserve the low frequency part of the spectrum of the signal. So this is a mathematical way to say, if we want to delete the signal, describe this signal with all the frequencies that it is consist of, and delete the parts that are bringing noise. The second part consists of the description of covariance and autocorrelation. Maybe this part will be very fast, because all of you will all of you know this part. So let's briefly skip this first introductory part about what time series is in the probabilistic world, and let's begin by the what we want. We want to understand if one series is repeating after a certain loop, and we want to understand if a certain series contains the same information of another series. The way to evaluate it is to evaluate the autocovariance of this series, and the way we do it is the sample autocovariance function, and we want to understand if two series are connected through the sample correlation. So these two objectives are met with these two sample functions, sample autocovariance function and sample correlation function. The topic that I wanted to stress instead is the length identification. The length identification, as I said, is a very difficult topic. I want to present you this paper, since it is focused on the big data context, and if you want to read it, I leave the detail of this paper. But the intuition of this paper is the following. I want only to stress the matrix profile the matrix profile how to say structure, in order to make you in the position to understand what the algorithm is doing. So what is a subsequence? Given a data series T, a subsequence IL is a series of value from T of length L starting from position I. Then, by this definition, we can give the second definition, and so the data series multipair. What is a pair? A pair is a couple of subsequences that have the minimum distance among all the subsequences among the ones that has the same length. And now we can define the distance profile. What is the distance profile? It is the vector composed by all different distances between all different subsequences. In this way, we can create a matrix that is formed by all the different distance profile, and now we have the structure to create the real algorithm. The real algorithm, I will give you only the graphical interpretation, because the paper is really, really complex, and I will need maybe other 2 meetings to explain you this algorithm. I want only to give you the interpretation, and the detail will be, if you want to read the paper, will be there. So all the different subsequences are analyzed with respect to all the others by going on to the real series T. So what is the intuition? The intuition is, if I have to make a comparison between the first series, for example, T119, and so the series that start from 1 and its length is 19. I have to compare to all the series that start from all the different points, but what can I say as intuition? That the subsequences T3319 and T33.9 are really, really similar. So since this concept is, since I can extend this concept to all the different subsequences in the series T, I can create all the combinations of similar patterns that I can find in the series T. After I evaluate all these distances, all these similar motifs, so the technical name of all these similar subsequences is motif, I can rank the different lengths according to the number of occurrences. So if the length 19 has 200 similar motifs, and the length 20 has 2 similar motifs, I say the most important length, window length is 19, since I make a comparison between the number of similar motif with length 19 and length 20, and I understood that the length 19 is the most recurrent one. So this way, this algorithm suggests you to identify as optimal length identification as the one that occur more and more in the original series T. This is only one of the many other approaches that you can find on the internet, on the other statistical book, but this is the one that I suggest you, as I said, since it is studied exactly for this, for the data science, for big data science objectives. So since we finish this section, maybe I will leave 3 minutes for any questions. Otherwise, I will start with the case study.
I think it's quite interesting. So you have, I didn't get the last point. So how do you tune in the end? You use this. I didn't get the point. How do you tune using the different possibilities?
Okay, maybe you are referring to the Valmod algorithm.
Yes, exactly. I use. I didn't get the measurement.
The measurement
On the y-axis.
No, the y-axis is the measure, and the
You say this is the
x-axis
time
is
series.
the t.
Okay. I didn't
is
get
the time.
Okay. Okay, it's one of the time series. Okay, now I was thinking that you have something related with the time and a certain metrics associated to the window.
No. T. Do you see my pointer?
Yes. I see that.
Okay.
Okay.
T is the whole time series, univariate time series.
That's the whole
And
interval.
then, okay. And then I want to understand what is the optimal length of the window. How to do it? I compare the frequency by studying the matrix profile. I want to understand what is the optimal length by studying the frequency of occurring of occurrence.
Yes. Yeah.
Andrea,
yes.
May I ask you a question?
Yes.
For example, if we said that the series of length 19 occurs, let's say, 200 times,
yes.
It means that also the sub-series with length 9 occur at least 200 times. In this case, it is better to choose the bigger one. How do we deal with this aspect?
Okay. Obviously, you have a window. This is a joke of words. You have a window of optimal possible lengths. So you can you go to the domain expert and you can ask him what is the optimal length in order to divide my time series and to do my clustering analysis. And the domain expert can answer you, well, I don't know exactly, but I know that the time series can be divided into windows of 9 until 19 length windows. So
okay.
You can analyze all these lengths. You have you create the matrix profile and you analyze all the occurrences. But you find that 19 occurs how to say 200 times and the length 9 400. You can understand that this is quite obvious if the length 9 is too small in order to capture some critical behaviors of the phenomenon that you are analyzing. But it is less obvious if the length is not too small to capture all these little behaviors. So the problem doesn't present if the range that your domain expert suggests you is really interesting for the phenomenon that you are analyzing. So maybe in this case, the signal is a bit noisy. But if you want to analyze some certain phenomenon about cars, you can give a specific interval that capture exactly the behaviors that you want to capture. And in order to do so, you will have the specific length, the exactly specific length, and you will not capture the noisy part that maybe you are talking about.
Okay, thanks. And also in the case of multivariate time series, we have to choose the length, taking into consideration the length that minimizes the distance also across the time series, because the length must be the same for all the time series, right?
Exactly. In the case of multivariate time series, I used a majority vote approach. So I used for example, we have 10 originally T series, and then I have optimal length window of 3 measures. So I chose the one that occur most between the 10 time series that I analyzed in a univariate approach.
Okay, thank you.
Nothing. Well, I will describe you the case study. The case study is to understand the duty state, the duty states of a car. And so not only and so I don't know what different behaviors a car can have, but I want to cluster these behaviors according to the techniques that I described in these meetups. So I will use Python and R, and then I will show you some scripts of these two. So, okay, let's begin by the dataset. The dataset consists of a series of CSV files that are recorded through the week of 2019 and 2018. Yes. I opened this data, and the columns are the following. So you can see that there is the day number, the vehicle, the trip number, so the number that identify a single trip, the timestamp. The timestamp is not cumulative, but start from the day number, but it is only a technicism. The position, the vehicle speed, the MAF, etc., etc., etc. the first thing that I wanted to understand is the days of activities and the length of this data set according to all the vehicles that we are analyzing. So we know that the vehicle ID is this number, so the index of this new data set. I understand that the 139 was an optimal vehicle in order to do this analysis. This is a car, and so I take this vehicle. I select only the data about this vehicle in order to do my analysis, and so I collect all this data in a proper data frame called data 139, and the first step that I did is a graphical representation of all the signals that are summarized in all the columns that I have in this data set. So the day number, the vehicle ID obviously is the same for all the series. The trip number, timestamp, latitude, longitude, vehicle speed, etc., etc., etc. What I noticed is that some series are not complete. So this means that some series have to be deleted in order to not add some noise. So for example, air conditioner power can have maybe 1 or 2 data, but are not significant in order to do a proper multivariate time series analysis. So I deleted all these not significant variables. And at the end of this graphical analysis, I understood that starting from all these characteristics, the ones that have a significant content are these 5. So the speed, the MAF, the engine speed, the absolute load, and the short-term fuel trim. And so I saved this data into the data 119 clean dataset, and I represent the dataset into with the index that is represented by the timestamp of the occurrence. And by columns, I have the 5 that I have chosen. So now I can do the same operation of the first part. So I graphically represent all the different series in the multivariate time series, and so we can see that they are fully they fully represent all the important period of the series of the multivariate time series. So this is the first part of the analysis, and I saved this clean data set. So this is only a preliminary part of this analysis. Second part. In the second part, I load this dataset, the dataset that I saved in the first part. Before continuing, any doubts? The situation is clear until now?
Yep.
Perfectly. In the second part, I add this column, the time difference, and this column allow me to understand what is the difference between one observation of a certain of a certain column with respect to the others. So why I'm doing this this step? It is necessary because in the real data there can occur different errors in the sampling part of the in the sampling part of the analysis. So when I'm recording data from a car, maybe the signal that is that I'm analyzing can be not so have a frequency that is not unique. There can be signals that are sent with a low rate or higher rate. In this case, we can see that most of the times, for example, we can see by this analysis, the time diff frequency is no. More or less, I don't want the median, but it is at least I have also the other graph that is okay. 100 millisecond is the time, is the mode of the different rate that I have between one signal, one signal and the other. So most of the time I have one signal, then 100 millisecond, then another signal, and go on and so on. But as you can see from the other graph, there are other errors that are very, very relevant in other part of the x-axis. So what I did, I understood that this part of the distribution of the time delta is considered as normal. From this point until this point, this is considered as as the vehicle is turned off and then on. So these parts are considered errors that that I will align to a unique time delta between one observation and the other. These others are considered as an exception, and so they are considered as the turn on or turn off the vehicle. According to this choice, I divided all the dataset into different big windows defined by this other column that is on-off, where on is where when the vehicle is turned on, I will set a 1, otherwise a 0. So this is a technique in order to fill not all the spaces with numbers, with occurrences, and to make all the analysis as clear as possible. In fact, indeed, all the theory that I explained in the theory part work better if the time difference is unique and not different for any any occurrence, for any occurrences. And so I decided to use this approach in order to align at least the big windows that are considered in a working cycle. So after this step, I deleted the noise that I explained in the first part. So I chose a low pass filter. Maybe I will give also I will give you also the code for in order to build a low pass filter. But the principle is the one that I explain you in the theoretical part. So I wanted to delete all the noisy part and to preserve the information part of all the different signals. In order to do this, I set the parameters of this filter, so the frequency, the cutoff frequency, and the order of the filter. And at the end of this process, I use this filter in order to clean these all the signals with a sample rate of 100. After this passage, I obtain these new signals, and so exactly the same columns of before. So vehicle speed, MAF, engine speed, absolute load, etc. But with a unique time difference, so a unique rate among the big windows that I select, and big space between the windows that are considered the working cycle of the vehicle. This is the last.
The frequency cutoff is decided by you?
Yes. Yes.
And
yes.
how
Exactly.
do you do it? So you decide it at random?
Okay. Yes. This is not an open question, but it is very, very difficult to understand what is the perfect cutoff frequency. Usually, you have to observe the signals and to understand when your phenomenon is clearer when you apply this filter. So you have this, you know the shapes of the signal when your behavior or your specific shape occur, and you can see also the raw signal. After applying different cutoff frequencies, so the main parameter of this filter, you understand when the signal can be identified in a clearer way. So this is the first approach. The second approach is more technical and consists of knowing a priori what is the specific frequencies, the specific frequencies that you want to analyze. So, for example, in the biomedical field, you can see, you know a priori what are the frequencies of a different phenomenon or a different behavior for all the different contexts. In this case, the cutoff filter is standard.
Okay, I was thinking something about, I don't know, the distance between the different frequencies. I don't know if my main and important signal is related with low frequencies. Maybe on the frequency space, I can see a distance between the the most important frequencies and the other ones.
Yes, maybe I didn't understand the question.
Yeah, no. What I was thinking is that maybe on your frequency space you have a certain difference of frequency between the main signal and the random signal, the noisy signal.
Yes.
And so maybe you can say, okay, where is my main signal, and I can identify seeing the difference between the different frequencies. I don't know if you see it.
Okay. Yes, I understood. Yes, maybe by measuring the distances between a correct signal and a noisy signal, maybe this can be an approach. So you have maybe the ideal situation, then you have your raw or noisy signal, and you want to set all the parameters in order to make the two series as near as possible. So yes, this can be done, but also in this case you have to consider the ideal situation. Yes, this is.
No, I was not thinking about the ideal situation.
You can do also with the noisy signal.
Yeah, no, but what I was thinking is that usually maybe you have I don't know, a peak in frequency at 10, a peak in frequency at 20, okay?
Yes.
And the third peak, for example, is at 60. Okay, so you see that the first two peaks are near, and the other peak related with the noise is very.
Oh yes.
Okay.
Okay. Yes.
Very far. So in this case, you can say, okay, I have a difference between the some part of the peaks, and there is a big distance between them. So I can say, okay, maybe these frequencies are related with the noise. I don't know. This is an idea.
Yes. This is a good point. Yes. In a lot of cases, the noise is concentrated in the tail of the frequency domain. Yes, and so you can also identify the specific window of frequencies that you want to delete, and you can set the parameters according to this. Yes, this is another approach.
Exactly. In fact, I think that if you have a big noise with a very low frequency, it's very difficult to analyze a signal in general. I don't know, but I think that it's very difficult.
Yes, this is true. Absolutely. But continuing to with this this notebook, we have also to understand another important data, that is the segment length, and so the one that I described in the algorithm of before. I will not show you the script because it is in C++ and it is in my other Ubuntu laptop. But the algorithm that I used was an algorithm given by the author of the paper that I know, and it is if you write to him, he can give you the code of this C++ code. In my case, the optimal length was 1,800 milliseconds. So I will use this data, but I will not show you what is the passage behind it. Simply because I did it in another laptop. But yes, by considering this parameter and the aggregation measure to 100 millisecond, that is the mode of the distribution of the time difference, I created the data frame filtered that I grouped also by windows. So the column windows is the one that for each observation indicates the window of which it belongs, and with the -1, I indicated the point that are not inserted in a specific window. Since the windows have a specific length, there are some occurrences that does not fit that do not fit into the window length, and so these one are deleted from the windows that I will analyze in the next part, and so they are not useful for this analysis. After this passage, I evaluated also the correlation, and when I did it, I noticed that the MAF is correlated with RPM and absolute load, and so I deleted it because the correlation was too high. They have exactly the same information, and so it is not relevant for the clustering analysis. And then also the RPM was deleted because it is correlated with absolute load and vehicle speed. So at the end, we end up with three signals. So we have a multivariate time series analysis, but with 3 signals, and this dataset is also divided into windows. For the next part, I switch to R. Why R? As I said before, because it has the libraries as CL valid, rank aggregation library, or DTW cluster that has all the functions that allow me to do in a proper way the clustering of multivariate time series. So from now on, I used a bunch of functions only that summarized the concept that I introduced during the last two lectures. So the CVI that I evaluated, the rank aggregation function, and all the algorithm with the distances that I explained in the first lecture. In particular, this function, the result fit clustering algorithm, evaluate the K-shape algorithm, the K-medoid algorithm, and the K-DBA algorithm in a range between 2 and 10 clusters. All these analyses have been done, and the final result is the following. So the K-medoid approach with a K equal to 3 has been selected. And this was also confirmed by all the parameters that I evaluated in the second part. So in order to do a clear analysis, I evaluated all the parameters between k equal to 2 and k equal to 10 for all the different CVI that I considered, that are silhouette, SF, CH, dB star, etc. According to these parameters, I evaluated the rank algorithm that gave me, as a result, exactly what I said. And so k-medoid with k equal to 3. In order to represent this result, I come back to Python and I represent it in two ways. This first way, maybe it is not really representative, since in the time domain scaled space, all these signals are really similar, as the one that I show here, or I can show here. They seem very similar. But the real graph that I wanted to show you is the following. This graph represents the mean of the Fourier transform magnitude in mean for each cluster, and for each measurement. So we have the vehicle speed, the absolute load, and the short-term fuel trim that we have considered. The first one in the cluster 0 has a strong component of low frequencies, as you can see in mean. Obviously, this is the magnitude of the Fourier transform in mean for all the series contained in the cluster 0 with respect to the vehicle speed. And the cluster 0 has a strong percentage of low frequencies, and also a strong percentage of high frequencies with respect to the other signals that we can find here. A similar behavior can be noticed in the in the representation of the absolute load. So we have a strong component of the low frequencies in the cluster 0 and cluster 2 for the absolute load, and a strong component also of high frequencies for the cluster 0 and the cluster 2. For the short-term fuel trim bank, we have a different behavior with respect to the cluster 0, because it has the lowest part of the low frequency. But we have the second cluster that contains in mean the windows with high frequencies and low frequencies more frequently. And this result can be summarized even better by the graphical representation. Maybe I can give you the full screen view. Okay. The representation of what I said before is reported also in this graph that represent in the x-axis a bench of windows in a specific part of the whole time series, multivariate time series. So between time window 1304 until 1310. And we can see that the cluster 0, okay, maybe I did that. Okay, cluster 0, that is the blue one, as I said, in the first series is really shaped both in the low frequencies and in the high frequencies. Not exactly the same thing in the absolute load series, and absolutely the lowest one with respect to the high frequency in this last case. Exactly the opposite for the red cluster. So in the red cluster we have, with respect to the vehicle speed, a strong a flat behavior in the vehicle speed series, a shaped behavior in the absolute load part, and a flat, almost flat behavior in the short-term fuel trim bank. That is exactly what I summarized in the graph that represent the frequencies. So these two graphs are extremely correlated. What I said about frequencies can be found also in the time domain representation. And with this notebook, I conclude the 5 chapters. So if you want to make some comment about this one, you can feel free to do any comments.
Yes, I hope that you will share with us this
yes, absolutely.
This notebook, so in such a way maybe we can use it for other things. But I think it's you did it in a very nice way, so it's very interesting.
Thank you. And this is really related to the conclusion that I will propose you in a few minutes. So yes, this is an hard work to do, but
yes, I saw.
Results can be found both in the graphical representation, both in the time frequency analysis, and so you have also the two parameters in order to understand if it is a good or bad cluster of multivariate time series. This is my favorite two representations.
Okay, and the code that you say that it was only in C++, it's not available in other languages, or you have only to integrate it in the C++?
I used a code of the author of the paper that I showed you before. I know him, and he gave me this code in C++. I use it, and then I didn't use anymore. So if you wrote to him, if you write to him, maybe he can understand the request. And
okay, so there is not there is any public code about this part?
No, unfortunately for this part, no.
Okay, clear. So if the other ones have some other questions, otherwise I think that we can conclude with the last part if you want.
Yes, this last part is only some take-home lessons. And so this is the final result summarized in a picture. And this is the last slide of my presentation. So this is 5 points that I want to stress on in order to make you a good clustering analysis for what concerns the multivariate time series. So the first objective is to study the space you are working in and have an idea of what you want to achieve. As I said before, the main actor can be the domain expert. Ask him whatever you want about the space in which you are working on and the objective that you want to achieve. The second important part is you want to understand the optimal aggregation rate in order to capture exactly the phenomenon that you want to analyze. So you can use a granularity of 10 milliseconds of 1000 milliseconds. Doesn't matter in an absolute way. It matters when you want to analyze some specific behavior of a certain phenomenon. Clustering need a lot of trial and error. This is the basis of this type of approach. So you have to try a lot of permutations of parameters, and you have to evaluate them with the validation CVI that I suggest you the way before, the last time in the last meetup. The last suggestion that I will give you is not to use too many clusters when you are doing a multivariate time series clustering. And the reason is simple. If you have 3 clusters, you can give an interpretation of them. If you have 30 clusters and you want to explain it to your supervisor, it is very difficult to interpret them. So this is the reason why I stop the comparison until k equal to 10. This is one of the main problem maybe to the clustering topic in general. So if you use a lot of cluster, also in other cases, not only in the unsupervised multivariate time series analysis, you will incur in the interpretability issue. So these are the main take-home lessons that I wanted to give you. And as I wrote at the end of this slide, enjoy. And thank you for the attention.
Thank you to you, Andrea. Thank you to all the people here, or that will see this meetup offline. And so I think that we can finish with this series of meetups. So thank you, really, I'm very grateful to you for your work, for all that you have explained during these meetups. I know that it requires a lot of work. Okay, so and I see that it's also very difficult. So thank you to have explained this difficult topic, and I think that maybe it's very important in general, because unsupervised learning is very difficult to understand. So I don't know, as I can say it, I can see the application of this meetup. So I think it's a very important topic from my point of view. So yes. If the other ones want to add some other things, otherwise we can stop for this evening. Thank you, Roberto. And so bye-bye. I can say that we can stop. So bye-bye, Andrea, and have a nice evening to everyone.